And of course, everything, well, that's bad. Everything on induction depends on our assumption, right? Because it's possible the assumption is wrong. So how could the proof be right if the assumption is wrong? Okay, so because assumption, we're trying to prove, what if something is not true? And we make the assumption, the basis could be true, the assumption could be anything we want it to make. You can try to make a false assumption to see what happens. So what we're going to do is we're going to look at the actual technique of proving something by induction. So for theorems, where you're trying to show that some statement is true for all n values, or specifically for what? N positive integers. So what we're doing is induction states that if we know that P1 is true, what's that? What does P1 is true mean? Basis. Okay, so if we have tested the basis, and we know that the proposition P of n implies P of n plus 1 is true, if we know that P of n implies P of n plus 1 is true for all n as part of the n integers, that implies that P of n is true. Now, when do we show that P of n implies P of n plus 1? When is that? Which step is that? No. That's the last step. That is the proof step. So we show, actually what we do, the assumption basically allows us to assume that something is true up to a certain point. That point could be j less than n, which typically means j at n minus 1. And then we got to show that it's true for n. So what we're trying to do is we're trying to show that P of n minus 1, which is the maximum assumption value, implies the truth of P of n. So P of n minus 1 implies P of n, and we say it's true. The other way of doing it is to assume that the statement is true for P of k, where k is arbitrarily large, and then show that P of k implies P of k plus 1. Well, it's the same thing. You're trying to show that 1 less implies 1 more for some values of n that are greater than the basis, that include all the values except for the outside of the basis, because the basis is proved directly. So mathematically, we can state it as like this. P of 1, which is the basis. Now this symbol means for all n values. Now for all n values could be for all n values in this set, right? And again, you can say, well, what about the 1? Well, 1 is true too. We can still include it. We don't have to exclude it. So we're saying that P of 1 is true, and for all n values that we're interested in, P of n implies P of n plus 1. So we're saying if this is true and the implication is true, that implies that P of n is true for all n values. For all n values. Any and all n values. Now let's think about what this means. So if P of 1 is true, that's a given because we're going to plug it in directly. So we assume that the basis is true. Now, we're completing the proof. We're saying that if P of n is true, then P of n plus 1 is true. So therefore, this has to be true in order for this to be true. Okay? So in order for the right-hand side to be true, then you have to have the basis true, and you have to show that the implication, the assumption, implies that P of n implies P of n plus 1 is true. That must be true. Which means that if P of 1 is true, then P of n plus 1 must be true. Okay? So now we're going to take this, and so therefore if we take this step is a given from the direct substitution, and this is true, that implies P of n is true for all values of n. So what we're going to do is we're going to prove that this is sufficient. Because right now I say, well, is it sufficient? Why is it sufficient to do that? Well, we're going to prove that it's sufficient by a proof by contradiction. Because you can't prove induction by induction, because that's begging the question. That's saying it's true because it's true. It's true because I said it there. Okay, so that can't be true. That doesn't imply that anything is true at all. So we will going to try to prove. So to prove induction by contradiction, we're going to say, suppose that this left side of this big implication is true. Which means that suppose that the basis is true and P of n implies P of n plus 1 is true. Suppose this is true and this is true, and it does not imply that it's true for all n. Okay? That's a contradiction. We're going to say, suppose that when this is true, then this is false. We're saying that when this is true, then this always follows. Suppose it doesn't follow. If it doesn't follow, then it doesn't imply that it's true. That means that it may be true for some, but there must be a value of n inside the set of all n for which this thing is false. At least one for it to be false. Because if it's false for one, it's false. You only need to find one counterexample. So we're going to use our proof by induction, and we will use the well-ordering property as an example, well-ordering property. Now, if we're proving induction for positive integers, what's the smallest integer? 1. And then 2, and then 3, and 4. Now, there's an infinite set of values, but there is a least value. There's a least value in this case. Now, if we had n is an element for, let's say, 0 and positive integers, then the least value would be 0. Typically, induction is done in such a case that you have some basis. That basis you plug in directly, you make the assumption, and then you continue to show that it's true for all cases. So there's typically a least value. That least value goes into our, again, it doesn't have to be 1. It doesn't have to be 1. It could be 0. It could be 2. Whatever is the value that we want to start at. But once we start, it continues. Okay, so the well-ordering property says that every set of non-negative integers, which is not empty, has a least element. A least element means the smallest element. So if we have a set of non-negative integers, non-negative means 0, 1, 2, 3, 4, 5. Every set that contains only non-negative integers has a least element as long as the set is non-empty. So now we're going to go to the next step. So what we're going to do is, again, if this is true and this is true, suppose that P of n is false for some value. Okay? That's the contradiction. Suppose it's false for some value. So therefore there must exist a positive integer where P of n is false. Correct? Okay, so there exists a positive integer where P of n is false. Now, S is a set of positive integers for which P of n is false. And if there exists a positive integer for which P of n is false, then S is not empty. Because it contains at least that one value for which P of n is false. So therefore, S, which is a set of non-negative integers, has a least element, k. And that element is the first value for which P of n is false. So we're saying P of k is false. That's the smallest element. Now, are you with me? Now, k, this value, this least element, cannot be 1. And the reason it cannot be 1, because P of 1 was shown by direct substitution. It's a basis. So it cannot be 1. So therefore, k must be more than 1. Again, and in our example, we're using positive integers, so that's why we're using P of 1 as the basis. So it cannot be 1, because we tried it. Now, k minus 1, so there is such a k, but k cannot be 1. Now, k minus 1 is also a positive integer. Okay? But k minus 1 is less than k. And since k minus 1 is less than k minus 1 cannot be an element of S, because the first element that makes the statement false is k, and k minus 1 must make it true. Which means that P of k minus 1 is true. Because P of k is the first one that makes it false. So the one previous to that must be true. So P of k minus 1 is true. But we have also proven that P of k minus 1 implies P of k. So therefore, since P of k minus 1 is true, we have proven that this implication is true. Therefore, if P of k minus 1 is true, that means P of k also must be true. And if P of k must be true, that contradicts the assumption that the smallest element that makes P false is k. It shows that there can be no least element that makes it false, given that we have the basis and the proof step of the assumption implying n plus 1. So the proof comes very quickly, doesn't it? Right? You do it, all of a sudden, boom, there it is. So we assumed that was a least element that was false, but assuming that element is equal to k makes it k minus 1 must be true. So therefore P of k minus 1 must be true. But we've also proved that if P of k minus 1 is true, that implies P of k is true. Which then, since this is true and the implication is true, that implies that if this is true, this must be true. So P of k minus 1 being true in the implication shows that P of k must be true. Therefore, assuming that P of k is false and k is the smallest element, which makes it false, is a contradiction. We cannot have a least element that makes it false, given that this is true and this is true. Therefore, this and this implication implies correctness. Questions? Got to think about it, right? You should think about it a little bit. You should think about it. It's one of these things like, whoa, where did that come from? But that's kind of how it works. So this is a proof of validity of proof by induction using contradiction as a technique. That's it. All right. So now that everybody's convinced and happy, or at least convinced, or at least happy, I don't know. If I'm happy, I'm convinced. If I'm convinced, I'm happy. So anyway, let's take a look at trying to prove algorithms, because we talked about proving some mathematical statements. Let's look at actually proving algorithms. In order to prove, and this is just something about sets, so I'm going to kind of skip around here. This is a set of 4 elements. It's a set of 1 element, which is the empty set. This is the empty set. And this is an infinite set, right, of the positive integers. All right, algorithms. In order to prove an algorithm is correct, we have to sort of know what the algorithm wants to do. And what the algorithm wants to do is generate a result. That result, typically, we describe as a postcondition. Meaning that here's the algorithm, we go into the algorithm, we execute the algorithm, maybe a loop or recursion or something like that, and when we come out of the algorithm, something is true. Always. Like after a sorting algorithm, we can say the data are in order. After a searching algorithm, if we determine the location of the element in the search space. If it comes back as null, it's not there. If it comes back as non-null, then it's there. Or true or false. So that value must always be true. So the postcondition is what happens at the end of an algorithm. A precondition is something that is assumed before the algorithm starts. So precondition is something we assume initially, and a postcondition is what is true about the result. Okay? So as a precondition, we may say S is a finite, non-empty set of values. Postcondition, max is a maximum element of S. That could be an example here. We also sometimes use these quantifiers. This is called the existential quantifier. The existential quantifier says there exists an X. Someplace there exists an X. Which one? I don't know. Exists an X. What does that mean? There's at least one. There exists an X, which is an element of S, such that the maximum is equal to X. And the universal quantifier means for all of X. So for all X values that are in S, max is greater than or equal to X. Okay, so those are kind of things we can state. Okay, let's take a look at an example of a factorial function. How many of you are familiar with factorial function? So factorial function is a recursive function, right? So what is the factorial of 3?
6.
3 times 2 times 1, or 1 times 2 times 3, which is going to be 6. Now, if the factorial of 3 is 3 times 2, which is 6 times 1, which is still 6, then the factorial of 4 is going to be 4 times 3 times 2 times 1, which is 4 times 3 factorial. So the 4 factorial will be 4 times 3 factorial, which is going to be 4 times 6, 24, and 5 factorial will be 5 times 4 factorial, which will be 5 times 24, which will be 120. So n factorial, in general, is going to be n times n minus 1 factorial. So that's kind of a recursive way to calculate factorial. So what we're going to do is we're going to use a recursive function, and then we're going to try to prove that it's in fact correct. So what I have here is I have a call where I send in some n, and n value comes in, and then n comes in, and then the return value is the factorial of n. Now, my precondition to make sure my function is correct is going to be that n is an element of 0 union, the set containing 0, union the positive integers. Well, that makes it the non-negative integers. So n must be an element of non-negative integers. 0, 1, 2, 3, 4, 5, like this. So, i.e. non-negative integers. The post condition is fact, which is a function, returns n factorial. Okay. Now, you understand the requirement for the precondition? If we didn't have the precondition, then what if n comes in as negative 1? Then we might have a problem. Because the function naturally is going to use the fact that a positive or non-negative value or a positive value factorial is going to be that positive value times the factorial of 1 less. And if my value comes in as n is negative, then we will return negative 3 times the factorial of negative 4. Negative 4 is negative 4 times the factorial of negative 5. We got a problem. Because now we're going to start going away. We want to start with values coming in a 4, or a 3, or a 2, or a 1, or a 0. That's the least value in here, least value. So therefore, if a 0 comes in, what am I going to say? That is 1, because by definition, 0 factorial equals 1. So if n is equal to 0, then we return 1. But if n is not equal to 0, what does that mean? Well, since coming in here are non-negative integers, and it's not 0, it must be a... What kind of integer? If the precondition says you can only come in as a non-negative integer, but it's not 0, so you must be what?
1.
Positive. What's the least positive integer? 1. So that means this is 1, or 2, or 3, or 4. It can never be anything less than 1. And so if this is 1, so we will return 1 times fact of 0. And if 0 comes in, condition is true, we return 1. That 1 gets returned into fact of 0, gets multiplied by 1, and then it returns 1 to here. So the factorial of 1 is equal to 1. The factorial, if I put in 0, 0 comes in, condition is true, 1. No recursion. But if you take a 1, it's going to go in here as a 1. Condition is false. We return 1 times fact of 0. 0 returns 1. 1. 1 times 1, we return 1. If the value is 4, here, 4 comes in, the condition is false. We return 4 times fact of 3. Condition is false. 3 times fact of 2. False. 2 times fact of 1. False. 1 times fact of 0. 1. It goes back to 1 times 1, which is 1. Then it goes back to the next level of the recursion. Because every time I call the function again, it's a different level of the recursion. So when we go in with a value of 4, we call this recursion level 0. So there is a special, the way computers take care of this recursion, they actually use something called stack frames. And a stack frame is basically a little piece of memory reserved for every function. So what happens is, if you have a main function, and the main function is here, main function calls f, then f gets its own stack frame with its own data. If f calls g, you get a g. When g finishes, it goes back to this f. When f returns, you go back to main. When main returns, you go back to operating system. So when you have recursion, let's say this function fact, so you have a main calls fact. Fact calls fact, fact calls fact, fact calls fact, fact calls fact. Finally returns the base case. So it returns the value where? To here. When this finishes, returns the value where? To here. When this finishes, returns where? To here. When this finishes, returns where? To main. Main prints the result. So it kind of goes like this, and then it unwinds back up again. So that's how recursion works. So you have the recursive level 0, recursive level 1, and as you go to deeper recursive levels, you get closer and closer to the base case. You get closer and closer to the base case. What's the base case? The base case is like the basis. It's the value that can be evaluated directly. So what's the base case in this particular function? When n is equal to 0. So the base case is if the parameter is 0, it returns 1. Why? Because 0 factorial is equal to 1 by definition. Okay, so we want to prove this is correct. It appears to be correct, but that's not a proof. Okay, so we're going to use an inductive proof. So basically, in order to prove an algorithm is correct, we have to literally walk through the code and substitute specific values at that point. So when you can see, so what we're going to do is we're going to look at the basis. So the basis for our proof will be the base case. And so in order to hit the base case immediately, you have to have n be past a value of 0. And so what I'm going to show here, the base step is n is equal to 0. When n is equal to 0, fact 0 returns 1. This is correct since 0 factorial is equal to 1. So when 0 comes in, the condition is true. We return 1. So fact of 0 returns 1. It's true because factorial of 0 is equal to 1. Okay, so the inductive hypothesis will be that factorial of j returns j factorial. So that's our P of j. Okay? And we will say greater than 0 because 0 is already covered. Now we could say greater than or equal to 0. It doesn't matter. 0 is already proved directly anyway. N less than n. So to show the proof step, what we're going to do is we need to show that fact of n returns n factorial. So now we're going to say now in this case, since n is not equal to 0, so now a big number comes in. So basically, remember, 0 we showed, then j can go up from 1 to a high number, so some big n comes in. How big? I don't know, 2, 3, 4, 100, 1,000, I don't know. Some big n comes in. So clearly, n is greater than 0. Why? Because it's not the base case. And it's the case if j is greater than 0. So since n is greater than 0, this condition for this big n value, this is false. So therefore we know we're going here. So we have to say this is false because we have to show that we're not going to return 1. So we know that basically n equal to 0 is false. Therefore the algorithm returns n times fact n minus 1. Right? Therefore the algorithm returns n times fact of n minus 1. Why? Because that's the code. By inductive hypothesis, however, fact of n minus 1 returns n minus 1 factorial. That's from the induction. Right? Fact of maximum value n minus 1 returns n minus 1 factorial. Are you with me? So therefore, since the algorithm returns n times n fact n minus 1, and fact n minus 1 by assumption returns n minus 1 factorial, we're really returning n times n minus 1 factorial, which is n factorial by definition, proving the algorithm is correct. By induction. Questions? Does that make sense? Hard, easy, straightforward? Any questions? What do you think, Scott? Good? All right, let's take a look at a binary search. How many of you are familiar with a binary search? Okay, so this binary search works like this. So basically, we have an array of data. So it's going to be smallest value increasing up to the largest value. Okay? And so what we're going to do is we're going to find out, we have a lower index and an upper index. We're going to find the middle location. We're going to look at this element right here. And we're going to say, is this the element that we're searching for? If the answer is no, we're going to say, are we looking for a bigger value or a smaller value? Because it's not a match. So if we're looking for a smaller value, since they are in order, it has to be not this one, but one less from the beginning to one less. But if it's a bigger value, then it's going to be the next one to here. So what happens is initially we are going from A to B, and this is the middle. If it's not a match, then recursively we'll go to m plus 1 to b, if it's bigger than the middle. Or if it's not bigger than the middle, it's going to be a2 m minus 1. So we're going to exclude the mth element in this case. So, so our precondition is a is less. Now, our indexing is going to be little a to little b. So a to little b. So the array big A is going index from A to B, is a sorted array. And the precondition is that A is less than or equal to B plus 1. Well, if A is equal to B, how many elements do I have?
1.
1. If A is less than B, how many elements do I have? At least
2.
At least 2. But this is A. If A is equal to B plus 1, so let's say A is 1 and B is 10. And then A goes to 2, 3, 4, 5, 6, 7, 8, 9, 10. How many elements?
10. At least 1.
1. 1 here. Now what happens when A goes here? How many elements are left?
Nope. 0.
0. Because how many elements are in an array? Upper index minus lower index plus 1. So if you have index, for example, 1 and 10, number of elements is 10 minus 1 plus 1, it's 10. When you have 6 and 10, 10 minus 6
4 plus 1. 5.
plus 1 is 5. 6, 7, 8, 9, 10, 5 elements. If you have 10 and 10, if A is moving on top of 10, then 10 minus 10
0
plus 1, 1 element. 10 minus 11 plus 1.
0.
Okay. So if A moves 1 to the right of B, then we have 0 elements. Okay. Now the reason we are interested, now why would A be ever bigger than B? And the reason for that is because we are recursing. So when we recurse, we're always moving, right? We're always moving things around. So our precondition is that array A to B is sorted with the low index less than or equal by 1 of the upper index. And the postcondition is found, which is the value I'm assigning, will be equal to the condition of X being an element of the whole array. So if X is an element of A to B, then found should be true. If X is not there, then it's going to be false. So the first thing we're going to do is we're going to call binary search on the array with the lower index, upper index, and the element we're searching for. And so the array comes in, the indexes come in, and the element that we're matching is X. If A is more than B, I return false. Why would I do that? If the lower index is more than the upper index, then there's no array. So therefore, if there's no array, if the search space has size 0, then you're not going to find it. False. So else means you have how many elements? What does else mean? At least one element. Right. Could be 1, could be 2, could be a million, right? We don't know. So therefore, if we have 1, then what I'm going to do is I'm going to compute the middle element by adding the lower and the upper indexes together and doing integer division by 2. And I'm going to pull that into mid. Then I'm going to, so mid element. So for example, imagine I have 1 and 10. If I have 1 and 10, that's going to be 10 plus 1 is 11 div 2. What's that going to be?
5.
5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be as close as we can to the middle. If it's 1 and 11, that's going to be 6. What if we start with 7 to 25? Well, it's going to be 25
32
minus 7, 18, 9. Right? So it will compute the middle as close as it can. And then what we're going to do is we're going to get that middle and we're going to check if the search element that we're looking for is match. If it's a match, then return true, which makes sense. But if it's not a match, then that element is not a match, so therefore lesser values are to the left of it and greater values are to the right of it. So in that case, if the element I'm searching for is less than the middle, then I really need to go to the left. which means I need to call binary search again with the same array, start still at the left side where it was before, but move the upper left of the middle element. Does that make sense? Now, if x is not smaller than the middle element, it must be bigger than the middle element, because we know it's not equal. Why? Because otherwise we wouldn't be in the else. Because if it was equal, we return. So we are here because we did not match, and it's not less than, so it must be greater than. Or if it's greater than, then it's greater than the middle, then the smallest element we want to consider is the one to the right of the middle. So that means our left element, instead of A, now becomes at mid plus 1 goes into A, but B is still the same. Does that make sense? So that's the algorithm. We want to prove that this is correct. And we're going to do it again by same technique. Okay. So the basis step is n is equal to 0. N is equal to 0, array is empty, and A is equal to B plus 1. Therefore, false is returned correct. So if the array is empty, we'll return false. And you can see here, because basically our low, here's the value. So if A comes in, is greater than B, remember the precondition means A is less than or equal to B plus 1. So what's the biggest value A can be? B plus 1. And when A is equal to B plus 1, A is bigger than B, we'll return false because there are no elements. So that's the case where n, the number of elements. By the way, n is equal to B minus A plus 1. That's the number of elements in the array. Upper index minus lower index plus 1. So if n is equal to 0, then we have a case where A is greater than B, we'll return false. We didn't find it. Well, you can't find anything in an empty array. So now we go to the next step. The inductive hypothesis says that for J greater than or equal to 0, less than n, and of course we certainly can say greater than what? We can say greater than 0. We don't have to say greater than or equal to 0. We can say greater than 0. Why? Because 0 has already been proved directly through the basis. So in this case, J is going to equal to, J is a value less than n, greater than 0, and J will be equal to nothing more than B prime minus A prime plus 1. What is B prime? B prime is the value of B in recursion level number 1. So for example, when we're coming in here, let's say my call is, let's say A is 1 and B is 10. So when this comes in, and obviously this is not a true statement, so the middle element will be equal to 5. So therefore, if this fifth element is not a match, and let's say this condition is true, then A will be 1, and mid minus 1 will be 4. So 1 will be A prime, and B prime will be 4. So B prime and A prime, A prime and B prime are the values of the first level recursion. When I say first level recursion, keep in mind when I send A in the first time, this is not recursion because I'm one function. This is just a function calling bin search. This is recursion because I am calling myself. So initially I am at recursion level number 0 because I'm not recursing, but once I recurse, I am a recursion of number 1 and 2 and 3, etc. Okay, so what happens is that J is actually equal to B prime minus A prime plus 1, and so therefore we're going to call bin search on the array using A prime, B prime, searching for X. Now, we're going to assume that for this level values of J less than n, that bin search of A prime, B prime, X correctly returns the value of the condition. X is an element of A from A prime to B prime. Of course, A prime to B prime is a subset of A to B, so therefore if it's an A prime to B prime, it's an A also, the array. Okay, so the proof of completeness is going to say, what happens when J is equal to n? So that means we're going to go 1 past this limit. When J is equal to n, clearly, this is a non-zero value, so this condition has to be false. So therefore, we have a value of m, so therefore we're going to compute the middle element. So how many elements, at the very least, does n have when J is equal to n?
1.
It has at least one element. But that's a very important concept. It has at least one element. Okay, so now we're going to compute mid is equal to a plus b divided by 2. Now suppose that it has one element, right? If it has one element, then a plus b divided by 2 is going to equal to what? If a and b are the same number, what's a plus b divided by 2?
Same.
It's a or b. It's the same. Okay, so therefore it's going to be the middle element. Now, so we're going to compute the middle element. If it's only one element, the middle element will be that element, right? So therefore, if x is equal to the middle element, which is the only element, we return true, which is correct. If it's equal to it, it's true, we return true. How do we know that? Because if it's equal, we return true. So if that one element is a match, we'll return true. However, if that element is not correct, if x is bigger than mid, okay, then it means what? That means that what's going to happen, we're going to go to the right. And when we go to the right, a is going to go to the right of b. Which means on the next recursion, we're going to return false. If the element is less than this value, then what's going to happen is b is going to go to the left of a. And we're still going to return false on the next recursion. So with one element, we're going to return correctly, right? Now what if the number of elements in J is more than one? For example, it's 2. If it's 2 elements, what's going to happen? Well, for example, let's say the elements are 3 and 4. So 3 plus 4 is 7, divided by 2 is going to be 3. So that means if it's not a match, if it's a match, we're good. But if it's not a match, if it's less than that, we have 0, which will return false. But if it's greater, then we're going to recurse with, well, how many elements? One element. And that means we'll have reduced the problem size by 1. And when we reduced a problem size n by 1, we are at size n minus 1. But n minus 1 is true, correct in the algorithm by assumption. Okay, so the proof of completeness says if j is equal to n, we compute the middle. If the middle matches, then true is correctly returned. But if the true doesn't match, if it's bigger than that, then x is an element of a from a to b only if and only if a is an element of mid plus 1 to b, which means we have reduced our size by 1. So if it was 1, it's going to be 0. If it was 2, it's going to be 1. If it was 4, it's going to be 2. We're going to reduce. And any reduction from m takes us down to at least n minus 1, which means that now this recursive call will be covered by the inductive hypothesis and will be correct. And of course, if x is less than a sub mid, we'll get the opposite here, right? It's going to be a member of the whole thing if and only if x is an element from a sub a to mid minus 1. And that's also a reduction of at least 1. Okay, so that's the proof of that one. Okay, any questions about these two? All right, so these algorithms that we looked at so far to prove specifically the binary search and the factorial function are recursive algorithms. Recursive algorithms are usually proved by induction. Recursion and induction are sort of hand-in-hand techniques. If it's a recursive algorithm, you can prove it by induction. However, some algorithms are not at all recursive. They are loops. We have 2 ways of repeating a set of instructions, either by iteration, which is loop, or recursion, which is calling the function over and over again. Now, actually, it turns out that iterative algorithms, looping algorithms, are more efficient, right? They're more efficient because what happens is, keep in mind, a recursive algorithm has to have a stack frame for every recursive level. So if you have 1,000 recursive level, that takes 1,000 stack frames in memory.
So it takes a long time to jump between stack frames because you have to access these variables. If you have a loop inside of a single function, that single function is only a single stack frame because you're not calling any other functions. You don't have to jump someplace and then return. So if you can do something by iteration, you're better off than if you do it by recursion. But some algorithms are very, very difficult, or even, I'm going to say, impossible to do without recursion. Other algorithms can be done by eliminating recursion. In some cases, recursion can be eliminated. In other cases, recursion is sort of an important part of the algorithm and cannot be eliminated. All right, so iterative algorithm has something very, very important, and then it's called a loop invariant. What does invariant mean? Invariant. What does that mean? Something is invariant, what does it mean? Doesn't do what? Doesn't change. Good. Doesn't change. Invariant. Loop invariant is basically a loop where the condition of the loop does not change. So the condition always has to be, let's say, true. So a loop invariant is a condition which is true at the beginning, before the first loop, and it's true before the last loop, then it goes into the loop, and then it comes out, and then now the loop is going to say drop out, you're finished, but before it says drop out, the loop invariant is true again. So loop invariant will be true before each loop iteration and before the iteration that doesn't happen because the loop is finished. That's what a loop invariant is. So now the loop invariant is going to capture a relationship between the variables which change, and actually the loop invariant will be a generalization of the post condition. So proving iterative algorithms is a little bit different than proving recursive algorithms. Proving iterative algorithms, we've got to do more work. You have to establish the loop invariant. You have to prove that the loop invariant is true. And now proving the loop invariant is true is just as hard as doing the entire inductive proof. Then you have to show that the loop invariant and what we call the break condition implies the post condition. And then you have to show that the algorithm terminates, because you don't have a base case, so you have to show that it's going to end. Because if it doesn't end, it's not an algorithm. So it's got to be finite number of steps. It could be 10, 25 billion steps, but it's got to be finite. It's got to have that finish. Okay, let's take a look at a simple example. Now, for this case, what I'm going to do is, if I do this on a test or on a homework, I'm going to expect you to simply be able to identify the loop invariant. I'm probably not going to ask you to prove it. I'm just going to get it right. Okay, so let's take a look. So I'm going to be very nice to you. But I want you to understand what it means. Since you already know how to prove recursion, you can prove this too. But and the notes show you some examples, but I'm just going to kind of go through it more quickly. Okay, so we have a precondition. The precondition is that my index, again, A is an array of values where the index A is less than or equal to B plus 1. Make sense? So what does it mean when A is equal to B plus 1? Array is empty. N is equal to 0. Okay, if A is equal to B, how many elements? 1. Very good. If A is equal to B minus 1, how many elements?
0.
2. How many elements in general in this array? B
A minus B minus A plus 1.
Upper index minus lower index plus 1. And never forget the plus 1, because if you have index go from 4 to 4, you still have the element, the fourth element together. 4 minus 4 plus 1. Okay, so the post condition is that sum is a variable is going to equal the array element aj as j goes from beginning to end. Does that make sense? Keep in mind that if a is equal to b plus 1, then the number of elements in the sum is 0, and the sum is 0. Okay, so this is the loop right here. The loop is underneath here. This is called initialization, and Li stands for the loop invariant. So I goes to A, sum goes to 0.
Now, when I do this initialization, how many times do I do initialization? One time. That means I do the initialization before the, which iteration? Before the first iteration. So that means before the first iteration, right before I go into the loop for the very first time, the loop invariant must be true. That means sum is 0 and I is equal to A must have some meaning. Now take a look at the post condition. The post condition says sum includes all the elements in A from A to B. Well, clearly what we're going to do is we are going to generalize that post condition so it becomes the loop invariant, and a loop invariant has to be true all the time. How many elements did we examine before the first loop iteration? How many elements did we examine before the first loop iteration?
1.
Before the first loop iteration.
Nope.
You see the red? We just got to the red after that statement above it. How many elements did we check in the array big A?
No.
0. So sum is equal to 0. Okay, sum could be 0 if you have some 0 elements. Okay? I is equal to A. What's A? A is the first element. What does I do in the loop body as we iterate?
Conditions increase.
I is being incremented. I is actually indexing every array element from A up to B, and perhaps it goes to B plus 1 to terminate, right? Okay, so what we have here is we can write the following, and I'll show you how we're going to generalize this loop invariant a little bit. So we're going to have I'm going to say sum. Now, notice that the value of sum at the end in the post condition is the sum of all the elements. But I am going to say sum sub 1 will be the value of sum before the first iteration. So sum sub 1 is equal to what? 0. Perfect. And I sub 1 is equal to what?
A.
Is equal to A, which also happens to be the first element. And so now the loop invariant must be true, right? Now, let's leave it at that. The loop invariant is going to have to be true right here. By the way, so it has to be true right here. Now we're going to do first iteration. So I'll call this here IT1, iteration 1, okay? And so now, what will the value of sum be? So sum will equal to what? This is sum sub 2 before the second iteration. What will the value of sum 2 be equal to? It will equal to sum 1 plus A sub, correct. A of I1, or we'll just say A, and we're going to say here, let's say A sub A, little a. But it is I sub 1, absolutely. And I sub 2 is equal to what? A plus 1. Now the loop invariant must be true. And now we start iteration number 2. Okay, what do we actually do in iteration number 1? What is the job of iteration number 1, which is those 3 statements? While I less than B plus 1, do sum is equal to sum plus AI, I plus plus. What do we do? What are we doing there?
Adding them.
We're adding into sum which element? The ith element. Okay, now after we do the last iteration, so we're going to call it iteration, how many elements do we have? I'm going to say iteration n, which is also known as iteration b minus a plus 1, right? So this is the iteration. We're going to have, after this iteration is done, this is going to be sum of n will equal to what? it's going to be equal to sum of n minus 1, the previous sum, plus
A of B.
a
B plus 1.
No, B.
Sub B.
B.
because that's going to add the last element when I finally increments to b. It's going to be sum, the previous sum, plus a sub last element b is going to be the new version of sum. This is the new version of sum, right? Now after that happened, what does the value, so what does the value of I become? So now this is going to be I. How many iterations do we have? This is iteration 1, iteration 2, iteration n. So what is the value of I? I sub
B.
n plus 1 is equal to
B.
B plus
b plus 1. Good. So I sub n plus 1 is equal to b plus 1. Okay. So now let's look at the post condition. The post condition, which is always given. So the big clue here is that the loop invariant will always be a generalization of the post condition with respect to the variables that are changing. Specifically, the variable that is changing is I. I is the key one, and sum is the other one. Sum is growing, and I is also growing. I is growing incrementally by 1. Sum is growing by the values of all the elements. So our post condition says that sum, which sum?
Sum n.
Because basically, notice that here, this is going to be before the nth iteration, right? Actually, I should say here, n plus 1. This should be n plus 1, because this is the sum before the n plus first iteration. There is no n plus first iteration. So we do that, well actually here, according to this, if this is going to be nth iteration, so I should do here, and I should do here. And then when we're finished, we're going to have sum at the n plus first iteration, and I before the n plus first iteration. So really what I should have done here is this really, let me correct this here. So before the nth iteration, it's going to be b, and this is going to be, before this one, it's going to be b minus 1. So now we go into the nth iteration where we grab that nth element, which is the bth element. So it's going to be sum of n plus 1 is going to be sum of n plus a sub b. And I sub n plus 1 is going to be at this point b plus 1. Now our post condition says sum is equal to the summation as j goes from a to b of a sub j. Which means that the post condition says that when the algorithm is, oh, now by the way, at this point, this is the value of the loop invariant right here, right? But what's the value? What's
right there.
so the value is true, but what's the value of I? N plus 1, b plus 1. So b plus 1 not equal to b plus 1 is? False, which means that this is the value before the n plus 1 iteration, but that iteration will not occur. We break out of the loop. So therefore, the break condition is when the continue condition is false. So the break condition implies what? So I'm going to write it here. The break condition, I'm going to put it over here, is what? I is equal to b plus 1. That's the break condition. That's the break condition. Okay. So now, let's take a look at what we have here. So what we want to do is we want to look at the loop invariant, and we want the loop invariant to be a generalization of the post condition. So therefore, it's going to be a sum like that, and it's going to be j is equal to, now the question is, where's j going to go from where to where? Look very carefully here. Before the first iteration, how many elements have we added into the sum? 0. Therefore, how do we show a sum of 0? Using summation notation. J goes from A. Now what must the upper index be?
B plus 1.
Same.
A
How we now this is going to be A sub j, right? What must the upper index be in order to get 0 elements in a sum? A what? No.
-1.
I heard one person say it.
-1.
A minus 1. A minus 1. Now, take a look at this. Where is A minus 1? We don't have A minus 1. We have I is equal to A. So therefore, we must be talking about I minus 1. So if you look over here, before the first iteration, the value of I is A. So the value of I minus 1 here is equal to A minus 1. How many terms from A to A minus 1? 0. That's correct before the first iteration. Before the second iteration, the value of I is what? Before the second iteration, the value of I is A plus 1. How many elements did we sum at this instance? 1 during the first iteration. So when I is equal to A plus 1, what is A plus 1 minus 1? A. How many elements from A to A?
1.
Okay. So now when we go over here, this is the value of the variables before the iteration, which does not occur before the break condition. So now what's the value of I? I is equal to B plus 1. So now what's the sum from A to B plus 1 minus 1?
B.
A to B, which is, by the way, the post condition. So what we need to show, and I want to show real quick here, is we need to show that the loop invariant and the break condition imply the post condition. So let's see what that means. So this is the loop invariant now, right? And this is the break condition. Okay? Right? So, if the break condition is true, the value of I is B plus 1. And if the value of I is B plus 1, then the value of I minus 1 is equal to B plus 1 minus 1,
B.
which is A to B, AJ sum, which is the post condition. So you can see the break condition and the loop invariant imply the post condition. Whatever you choose as your loop invariant, it better be true before the first iteration. That's the key. If you can't get that right, it's not the loop invariant. And you can see here, sum is 0, I is really A. So therefore, the only thing we can have here is since we're summing 0 elements, we have to make sure we're starting at the beginning, but we cannot include one single element. So we can't go I to I, because that would be A to A, that would be one element. So we go A to I minus 1. And here, you can see that I goes to B plus 1, and then if I is in fact B plus 1 from the break condition, then B plus 1 here implies the post condition. And that's the way it works. Okay, any other questions about that? So that's those type of problems. What I'm going to expect you to do is I'm going to expect you to not to prove that, because the only thing we haven't done here is we haven't actually proved that the loop invariant is correct. That has to be done by induction, and it's not pretty. It's a lot of work. It's not too bad. I mean, I show you how to do it. You can see over here, you can see how I do it. So again, it's going to be a basis, inductive hypotheses, and then proof step. But I'm not going to ask you to do it. But I will ask you to get this right by trial and error, trying it to make sure that it's going to be correct. Yes, sir?
So it was written there that for summing algorithm, every condition should be true, right? So
The what condition?
every condition should be true.
Precondition. Precondition must be true before the algorithm starts, yes.
So wouldn't it sum up to be an infinite loop over there?
Why?
Okay, so can be the previous line? It's written somewhere there.
Well, first of all, if A is equal to B plus 1 initially, right? Then the condition will be, the break condition will be true initially. Right? That's okay. So if A is equal to B plus 1, then the break condition is true initially. We know the loop invariant is true, so therefore the break condition and the loop invariant will imply the post condition. Okay, so this is a proof step. This is another algorithm showing this one's a little bit more complicated. Even though the algorithm is very simple, you can see that the tricky thing about these types of proofs is that you have to worry about indexing the I and the whatever variables are changing. You have to index them before that iteration. And that's what makes it a little bit more confusing. But and that's why I'm not going to spend too much time on it. Okay, so that's, I'm going to finish here on that, and I'm going to go to the next section of our notes. Okay, so this is section 2. This is algorithm analysis. So we're going to go, the first one is part 1. This is part 2. We're going to go to part 3 next, which is the mathematical tools and things like that. Okay, so the algorithm analysis, basically, we're going to be analyzing algorithms. We're going to be analyzing their efficiency. We're going to be analyzing their complexity. So we should know what the heck is complexity anyway. Sometimes people talk about performance of an algorithm. This algorithm is outperforming another algorithm. Well, performing is a very difficult thing to quantify. You could have one algorithm outperforming another algorithm, but that simply means it's running faster than another algorithm. And that doesn't prove that it's a more efficient algorithm. You can outperform another algorithm and not be more efficient. And how is that possible? It's possible because when an algorithm is running, it's running on a particular input. And you can't assume that every algorithm will run the same for all sizes of input and all permutations or orders of data on that same size input. So it's a very tricky question, what we're talking about. Performance simply means, think of it as car racing. If a car wins a race, it's better performance. That means it gets to point B faster than another car. But maybe in another race, it gets there slower. So what's going on here? So algorithms, sometimes two algorithms are working, and let's say one is going to be finished first. So this is better because it's finished already. This one's still working. But then you give it another data, for example, and they're very close, and maybe even this one wins a little bit. So which one is better? Well, again, what changed? The data changed. Maybe more data. Maybe the data is more difficult to process. We don't know. So we have to take those things into consideration when we talk about performance. When we talk about complexity, complexity is a simpler idea. Complexity is essentially saying that a function has a lower complexity. A function has a lower complexity if you take the limit of that function with n going to infinity, and if that value is bigger than another value, if that one goes to infinity and this one goes slower to infinity, then the one that goes quicker to infinity has what?
More
A higher complexity. And the one that goes slower, it's got a lower complexity. So we look at the big input, at the big values that can make a difference. So complexity means what happens when the input becomes really, really big. And really, really big could be only 100 or 1,000 or 50. Or it could be 10 million at some point in time. So typically, if you have functions that are polynomial functions, those polynomial functions, the lower the degree of the polynomial, the lower the complexity. Quadratic functions are lower complexity than cubic functions. Cubic functions are lower complexity than fourth power functions. Quadratic functions, second power, are lower complexity than 2.1 power functions. As long as the exponent is increasing, the function is getting more complex with polynomial functions. Not all functions are polynomial. We have polynomial functions that could be linear, quadratic, cubic, quartic, which is fourth power, fifth power, etc. But we also have other types of functions, logarithmic functions, exponential functions. We have linear times logarithmic. We have different bases of logs. We have different bases of exponential functions. We have square root functions. We have combination functions, square root divided by log n. That's a function. Now, is that a better complexity than n? Well, you better know that. Well, not now, but you need to be able to calculate that and figure it out, how to solve that. Okay, so let's talk about algorithms. So let's say we have an algorithm, which is a famous algorithm called bubble sort. How many people have heard of bubble sort? Raise your hand if you've heard of bubble sort. Okay, so for those of you that haven't, or even if you have, I'll just review very quickly. There's two ways of doing bubble sort. Basically, it's a pairwise comparison. So let's say you have data of a bunch of numbers. You're going to try to sort those numbers. So let's say you have 10 numbers. So you compare 1 against 2, 2 against 3, 3 against 4, 9 against 10. Every time that you have a smaller number, bigger number on top, you flip it. So 1 and 2, if the bigger number is on top, you flip it. 2 against 3, you flip it if it's bigger. If not, leave it alone. Leave it alone, leave it alone, flip it. Flip it, leave it alone, flip it. Leave it alone, flip it. Okay, so what happens is, whenever you encounter the biggest number, and that biggest number ends up being on top, it's going to flip down. And then when you go down again, you're going to flip it down again and flip it down again. So after comparing all the numbers, you do what we call one pass through the numbers, and the biggest number will end up going to the bottom of the array. That's a bubble sort. Sometimes people like to do it this way, and then the smallest number comes up, but it's the same idea. So the bottom line is, after one pass, after all the comparisons of all the adjacent numbers, one number is exactly where it should be in terms of being sorted. So in order to sort the array, we need to now start again. And someplace we'll catch the second biggest number, and it'll start flipping, and it'll go right above that one. When we do it again, we have 3, we have 4, we have 5, we have 6, we have n minus 1. Once we have n minus 1 perfectly placed, we have n perfectly placed. Because where's the n going to go? It's going to be by default in the right spot. So the bubble sort, essentially, how many statements does that, how many statements are going to execute? Well, statements are comparisons. Those are the instructions that we focus on. And you can see if you have n numbers, you compare 1, 2, 2, 3, 3, 4. So that's 1, 2, 2, 3, n minus 1, n. So it's really n minus 1 pairs. N minus 1 is very close to n. We're going to say, roughly speaking, for one pass, you need n comparisons. It's really n minus 1 comparisons. But then you got to do the pass again, and again, and again, and again, and again. You got to do it n minus 1 times, roughly speaking, n times. So bubble sort requires roughly n squared comparison statements to sort n elements. And let's say it requires those n squared statements to sort n elements. And let's say you can do it in time interval t. So let's say t is 10 milliseconds. Okay? So let's say I can sort n elements in time t. If I can sort n elements in time t, that means I must be executing n squared statements in time t. Does that make sense? Now you can say, well, what do you mean n squared statements? What about okay, I'm going to say, forget about n squared statements. How about cn squared statements? Some constant times n squared. Okay, because sometimes I compare, I have to swap, swap, swap. Sometimes I compare, I don't have to swap, swap, swap. So if I just multiply by constant, I'll be okay. So cn squared is good enough, but we can just simply simplify it to say n squared statements. Now, so how do I go here? So if in time t, I know I can execute n squared statements. Because the complexity, or the proportional number of statements that need to execute in bubble sort, is n squared. Proportional means cn squared, some number of n squared, right? Some coefficient times n squared. So I can execute n squared statements in time t. So if I ran 2t time, how many statements would I execute? If I can execute this many statements in time t, how about in 2t time? 2n squared. This is not a hard question, right? Now, okay. Now, all right. Now, suppose. Now, how fast is my computer? My computer is so fast. How fast? So fast. Just whatever it is, that's what it is. But suppose I took my computer and I increased the speed by 1 million, which would be really nice if we could do that in real life, but we can't. But we can do it in fake life, so this is fine. So we're going to increase the speed of my computer by 1 million. What that means is, before in time t it executed n squared statements. But now, since it's 1 million times faster, in the same time t, it will execute 1 million n squared statements. Does that make sense? And it executes 1 million n squared statements. But the question is, how many elements can it bubble sort in time t? And the answer is, to compute the number of elements it can sort, you can see that the relationship between the number of instructions, number of elements, is going to be the square root of the number of statements will be the number of elements. So since the new speed up gives us an opportunity to execute not this many statements, but 1 million n squared statements, the square root of that is going to be 1,000 n. 1,000 n. So I can now bubble sort 1,000 times bigger array, even though my computer is 1 million times faster.
So I've increased my computer speed by an order of 6 magnitudes, but I've increased my problem size only by 3 orders of magnitude. And the reason is because the complexity of bubble sort is not linear. It's n squared. And so the relationship to the problem size and number of statements is you square it to get it's quadratic. So to go backwards to the problem size, you take the square root, which is the inverse of the complexity. And the inverse of that complexity is going to be the squared increase. So you can see what happens here is that even though my computer should be solving 1,000,000 times faster problems, but because the complexity of the algorithm is quadratic, I only get 1,000 times increase in the problem size. Okay, does that make sense? Yes, no, maybe?
Yes.
It doesn't make any sense. All right, so I'm almost done. I know what you're saying. Are you done? Okay, so very quickly, just look at this. So we have another algorithm that's called a swap down, and it's part of a heap sort algorithm that we'll study later on. And that one requires LGN statements. So LG, anybody know what LG is? Log base 2. So it's like log2. So LG is log base 2 n statements for n elements. So the formula for going from n to the number of statements is you take the log of the number of elements. How do you go from LGN to n? So this is going to be the size of the problem. This is the instruction count. How do I go from instruction count back to the problem size? I have to do the inverse of LGN, which is exponentiate with the base of 2. So I have to raise 2 to the power of LGN is equal to n. So therefore, okay, so now, if my computing speed is increased by 16, then I can execute 16 times LGN statements in the same time t, correct? So therefore, how about what kind of problem can I solve? Well, the problem I can solve is going to be what? It's going to be, I'm going to need to, so I'm going to have 16 LGN, which is LGN to the power of 16. If I take a 16 here, 16 times log of n, that's equal to log of n to the power of 16. And so therefore, the problem size I can solve now is going to be n to the 16th power. N to the 16th power. So I speed up my computer by 16, but the problem size increases by an order of 16 power, n to the 16th power. So if I could solve a problem of size 1,000 before, now I can solve a problem of size 1,000 to the 16th power. It's 1,000 times itself, 16 times. So you're increasing by 16, but you're able to solve this big a problem in the same time. Why? Because the complexity of this algorithm was way below linear. So the speed up you get is magnified because of the instruction count, is logarithmic, and so you can see that the problem is increasing exponentially. And the last example I'm going to give you is, suppose that you have to go through the array. And what you're going to do is you're going to just do some computation on each element like this. So let's say you can process n elements in time t. But you need just a linear, just one-time access to them. So you don't have to go twice like bubble sort. So what you're going to do is you're going to go through the array. You're going to do n elements in time t. Now you speed up your computer by 100. So now you can execute 100 more statements in time t. So instead of n statements in time t, it's 100n. But since you're doing the same linear complexity algorithm, how big a problem can you solve? 100n. So you speed up the computer by 100, you solve a problem 100 times bigger. So if the algorithm is linear, that means you need one access to each element exactly once, then your speed up will be on par with the problem size. If your algorithm is high complexity, then your speed up will be reduced by the inverse function. Reduced by the inverse function. So quadratic, power of 2, square root. Cubic, power of 3, cube root.
If your problem is sublinear, like logarithmic is very small, right? Log base 2 of about 1,000,000 is about 20. Log base 2 of 1,000 is about, base 2 of 1,000,000 is about 20. Log base 2 of 1,000 is about 10. 1,000, double it. 2,000, 4,000, 8,000, 60,000, 64,000, 128, 256, 512, and before you know it. Okay, so if your algorithm is sublinear, less complex than linear, then your speedup will be increased. Your speedup will increase the problem size higher than the speedup. So it's very, very important to be aware of these things as we study algorithms. Okay, I'll see you on Wednesday.